And with that, that actually covers all of our different types of alkyne chemistry. A lot of it is the same stuff that we see with our alkenes, just with just a little bit of kind of like extra nuance associated with it. So just as we saw in our very first video, our very last video is just going to be kind of our summary table looking at each of these different types of reactions. Our very first one is going to be a reduction, or adding hydrogens. We got 3 different types of reduction reactions. We can use metal catalyst like a palladium, a platinum, or a nickel with hydrogen gas, and that will give our syn addition all the way down. That's a full reduction. We also can get partial reductions from triple bonds down to double bonds. There are 2 different ways we can do this. The first one is going to be a syn addition, meaning that we're going to get a same side, or our cis double bond. This is most commonly done through Lindlar, which is going to be our palladium catalyst that's poisoned by something. Doesn't matter what, just say Lindlar. And then the other version is going to be our metal and ammonia. This is going to be a radical reaction that's going to give us our trans addition of our H's, and that's going to go from a triple down to a double. Key thing to note here is that metal ammonia is not your sodium amide. Those are 2 separate things. We can also do halogenation, whether that's a hydrohalogenation or a full halogenation. That would be using something like an HBr or a Br2. You do the same thing with chlorines, for example. If you use HBr, you do need to consider Markovnikov additions where possible. If you have your internal triple bonds, those can form kind of a mess. Here, your stoichiometry will do a bunch. If you use 1 equivalence versus excess, you can get a single addition or a double addition. Exact same thing with your halogenation. Br2 is going to form like a bromonium. That bromonium will open up, giving you an opposite addition or an anti-addition, and then you can do that in excess to add a lot of bromines. We have a 4-bromo species there at the bottom right. We can also do hydration. These hydration reactions are going to be the ones that undergo our tautomerization or our ketoenol. We got 2 choices, either using mercury or using boron. Mercury is going to be our Markovnikov, and our boron is going to be our anti-Markovnikov. Each of these are going to form an enol, which is going to be taking that triple bond down to a double bond, then adding an OH to your Markovnikov or anti-Markovnikov spot, depending on which one you're doing. And then that's going to tautomerize to your ketone or your aldehyde. Here I have examples of your terminals, which are nice and easy because there is a Markovnikov or anti-Markovnikov. If you have an internal one, you will actually get your ketones at both your left and right side because there is no preference. So these can also be messy, much like you see with your halogenations, as we mentioned above. The last set of reactions are going to be our oxidations, and there's a bunch of different ways that we can kind of think about these. In general, we're going to be using KMNO4 as our oxidant, and if we're using neutral reactions, so this is typically going to be cold, typically going to have like nothing acidic or basic, instead just neutral water. These are going to form additions of your ketones. You actually form multiple alcohols, but those remove as water. If it's internal, you'll get a diketone. If it's at the end, then what you'll do is that end part, instead of becoming an aldehyde, gets fully turned into a carboxylic acid. If you use harsher conditions, you'll get that ozonolysis or like that cleaving like reaction. And those will be ones that will typically use heat and base. If you have internal ones, you'll cleave directly on your triple bond and you'll form carboxylic acids on both sides. If it is a terminal, that will generate a CO2 on your terminal side, and it'll look like your molecule just gets kind of shorter by 1. Here, these all examples were all with KMNO4. You can also do this with ozone. If you use ozone at negative 78 degrees, which is going to be in a dry ice and acetone bath, do note that negative, kind of like got a little bit funky there. Oh, and it still got funky. That is negative 78 degrees C in a dry ice acetone bath. And then quench, you can do this same thing. So those are our kind of slew of different reactions, all kind of similar to what we see in our alkene, just using kind of like just one extra step with regards to our alkynes. So that's going to wrap up our kind of virtual lectures for our alkynes. The goal here was just to kind of give you a good amount of exposure. All we're going to be doing in class is a ton of practice problems, looking at these and drawing some mechanisms and things of that sort. But we wanted to kind of give you the kind of like high-level overview of all of our different types of reactions. That way we can start putting them together and actually making some cool products and doing cool reactions with our alkynes. So with that, I hope you guys have a good one, and I'll see you in class.